Did you know that the original Golden Gate Bridge collapsed during an earthquake in 1906, thus removing an essential crossing above the Golden Gate Strait? We're not sure when and how the older bridge was built. However, there was one, and it collapsed in one of America's worst natural disasters that took place on April 18, 1906. It flattened half of San Francisco and caused fires that devoured the other half. Nevertheless, the resilient people of San Francisco rebuilt their city, but had to wait until 1937 for the new Golden Gate Bridge to become a reality. This new bridge was, and still is, a majestic world-famous landmark and an engineering marvel. Deliberations to build it took 14 years because far too many skeptics believed that it is simply a bridge that cannot be built to the harsh weather conditions, cost, water depth, and fear of earthquakes. However, it was built between 1933 and 1937 at the cost of $35 million, the equivalent of about $1.3 billion today. What's the special story behind the Golden Gate Bridge? How was it built? And why is this colossal historic bridge so unique in its design and engineering? In 1919, after much of San Francisco and Marin County were rebuilt and returned to their previous glory, a decision was made to restore a critical connection between them over the Golden Gate Strait. However, that decision did not translate into the actual construction of the bridge until January 1933, when the construction of the Golden Gate Bridge finally began. At the time of completion, it was the longest suspension bridge in the world, and it maintained this position for nearly 25 years until New York's Verrazano Narrows Bridge opened in 1964. Today, as the bridge celebrates its 83rd birthday, it is still the second longest suspension bridge in the USA, and the fifth most admired structure by American architects. During the working week, over 120,000 vehicles drive over the bridge, and it was closed only 3 times since its inception, mainly due to extremely windy conditions. The bridge is 1.7 miles long, 90 feet wide, with 6 lanes for vehicles and 2 sidewalks for pedestrians, and the center span deck is about 220 feet high above the water. It can accommodate up to 1,200 cars at once, which means it can easily handle 3 million tons of weight, pushing down on the suspension system during rush hour. On May 24, 1987, the bridge was closed to vehicles for its 50th anniversary celebrations, and only pedestrians were allowed. On that day, 300,000 people gathered in the middle span. The crowd was so dense that the span actually flattened. It literally dipped 7 feet. But guess what? That was totally fine because the bridge is designed to sway side to side 27.7 feet and flex up and down 10.8 feet. It is such a meticulously designed bridge, even if one piece of the deck plunges, it doesn't cause a domino-like effect that would see other sections collapse. Designing the bridge started in 1919, and it was not an easy task. The chief designer and engineer behind the megastructure was Joseph Strauss, a legend in the field. Back then, they had no computers or even simple basic calculators because such technologies had not been invented yet. Amazingly, they would rely mainly on slide ruler calculators, which enable engineers to multiply and divide based on logs and to determine squares, roots, common logarithms, and trigonometry functions. In comparison, today, engineers have access to advanced, sophisticated calculators and computer software that does all sorts of magical calculations and other things, including accurately determining issues related to pressure, resistance, aerodynamic functions, feasibility, structural integrity, and even producing results of tests without having to create models or conduct physical experiments. The initial design by Strauss for a bridge was a hybrid bridge, with a suspension span supported at each end by cantilever trusses. However, by 1929, consulting engineers Leon Mosaif and O.H. Amon had persuaded Strauss to accept the more graceful all-suspension bridge design, which is the one we see today. The blueprints were soon ready, and all they used were slide rulers, pencils, paper, and drawing boards. The result was an engineering marvel, a good-looking, impressive mega structure that can withstand extreme weather, immense weight, and severe earthquakes. To ensure the soundness of their design, they built a steel tower model of 1:56 scale and found that their calculations are good to go. Additionally, the geology of the South Tower location was investigated before construction could begin. The consulting geologist, Andrew Lawson, was hired to conduct a load test by placing weight equivalent to a fully loaded railroad boxcar on an area of serpentine rock only 20 inches square. The construction began on December 22, 1932, with the building of a 1,700-foot-long access road to the construction sites of the Marin Side Anchorage Pier and Tower. Once the road was ready, the official construction of the Golden Gate Bridge began on January 5, 1933. In February 1933, work began on the East Approach Road from San Francisco that extended through the Presidio to the south end of the Golden Gate Bridge. In March 1933, colossal amounts of prefabricated steel for the San Francisco and Marin towers were brought by flat car from the manufacturers in Pennsylvania to Philadelphia and transferred to barges, then shipped through the Panama Canal to Alameda, California. By March 1934, the San Francisco Tower access trestle was ready, extending 1,100 feet offshore. However, in August of the same year, it was damaged when the McCormick Steamship Line's Sidney M. Hauptmann crashed into the access trestle. It was repaired, but damaged once again due to strong winds and once again repaired. Marin's side tower was completed in 1934 in the same month. The San Francisco Pier area within the fender wall was unwatered. Construction workers pumped 35.6 million liters of water out of the fender, and by June 1935, the San Francisco side tower was ready. The following step was to install the cables. The company Harbor Tug and Barge strung the first wire cables to support the catwalks, in preparation for the main cable spinning. By October 1936, the main cable spinning and compression were complete. Finally, in November 1936, the two sections of the bridge's main span were joined in the middle, and a bishop blessed the span while sprinkling holy water. In April 1937, the roadway was completed. The final product was a stunning, majestic bridge that attracted envy and respect from across the world. The total length of the bridge, including approaches from abutment to abutment, is 1.7 miles. The length of the suspension span, including the main span and side spans, is 1.2 miles with a distance of 4,200 feet between towers. Each side span extends 1,125 feet. The two main towers each rise 746 feet above the water and 500 feet above the roadway. The weight of the original reinforced concrete deck and its supporting stringers was 166,397 tons. However, after the deck was refurbished in 1986, the weight of the new orthotropic steel plate deck, its 2 inches of epoxy asphalt resurfacing, and its supporting pedestals became 154,093 tons, about 12,300 tons less than before. The bridge is quite amazing and has some quite intriguing deflection and load capacity features. The midspan has a down deflection, meaning it can move downwards from weight and pressure 10.8 feet, while the upward deflection by as much as 5.8 feet. It can also sway side to side up to 27.7 feet. The two main cables pass over the tops of the two 746-foot tall towers and are secured at either end in giant anchorages, while on top of the towers in huge steel castings called saddles. The Golden Gate Bridge has 250 pairs of vertical suspender ropes that are spaced 50 feet apart across both sides of the bridge. These ropes were also replaced between 1972 and 1976. In 1954, after the addition of the lower lateral bracing system, engineers found that the main cable band bolts have lost as much as 50% of their specified tension. As a result, the main cable bolts were retensioned and constituted the first application of calibrated impact wrenches for the tightening of cable band bolts. In 1975, during the replacement of vertical suspender ropes, the cable band bolts were again retensioned to 90,000 pounds using a Biach hydraulic bolt tensioner. This work was performed from ironworker floats hung below the cable. Today, this bridge stands as a witness that mega projects do solve problems, enhance economies and social connections, and with the right design and engineering, innovations can withstand time and